In this lecture, we will discuss about multi-element airfoils, laminar and turbulent flow past airfoils, and a little bit on airfoil trailing edge noise. So, in the previous lecture, we discussed about the effect of flap deflection on lift coefficient, where this was the trailing edge flap. It was deployed from the trailing edge of the airfoil, and we discussed about the positive and the negative deflections. So, the positive deflection, which means deflection downwards, moved the CL alpha curve upwards, thereby increasing CL max, and the upward deflection of the surface led to parallel movement of the CL alpha curve downwards. And then we discussed about the implications, and we also talked about how it would involve a difference in the stall velocity of the aircraft. Of course, remember that when the airfoil section is applied on an aircraft, it is applied on a finite wing. It is not on an infinite section, and therefore, the end effects of such a finite wing would influence the aerodynamics, which we will see in later lectures, but for now we are concentrating more on the sectional behavior of such a wing. Thereby, we are looking at the airfoil characteristics. Let us now look at leading edge flap and its influence on lift coefficient. So, this time we are discussing about deploying a flap close to the leading edge of the airfoil section. So, this is when it is retracted, and therefore, the airfoil looks like a single element, but in this case the lower figure shows the flap deployed. We often call this as a slat as well. So, what is the influence basically on the CL alpha curve? We see that broadly speaking, the alpha stall increases, and there is also an improvement in the CL max as a consequence, because of deployment of the leading edge flap. But there is no major shift of the CL alpha curve either upwards or downwards, like what we saw in the case of trailing edge flap. So, if we sum up the effects of the trailing and the leading edge high lift devices, we see that they are designed to increase the effective angle through which the flow is turned when it comes to the trailing edge high lift devices. That means, they increase the camber. Consequently, there is an increase in the lift force. While leading edge devices are basically designed to assist the flow in negotiating the sharp turn from the lower surface when the flow moves up. So, if you look closely at the nose region of the aircraft or the airfoil, and if the flow is approaching at a considerable angle of attack, then there is a very sharp turn that the flow has to take to reach the upper surface and remain attached to it as it does. This is a real flow, and therefore, the viscous effects are very much dominant in this case. We have to be very careful about keeping the flow attached as it encounters that sharp turn from the lower surface around the leading edge, and it should not be separating due to the sharp turn. This problem is more adverse at high angle of attack, or it could be even adverse at low speeds, because at lower speeds the boundary layer is expected to be by and large laminar near the leading edge, and it is more susceptible to separation than a turbulent boundary layer. When leading and trailing edge high lift devices are deployed simultaneously, we talk about a multi-element configuration, because now the airfoil looks more like a leading edge flap here, the main part of the airfoil section, followed by a trailing edge flap, and therefore, you have multiple elements which are deployed in order to create the desired effects on the flow, which augments the lift and reduces the stalling velocity and improves its performance at lower speeds. So, there we deploy the multi-element configuration, while when it is cruising, when it is at a much higher altitude, when it is flying in straight level flight, then these multiple elements are retracted back, and therefore, you would see the airfoil as a single element by and large. So, they are utilized during the takeoff and landing phases of the aircraft when high values of maximum lift coefficient is desired, and therefore, adequate lifting force is generated, and that is generated at comparatively lower speeds, which could be close to stall speed. Now, the flow through the slot that we just saw energizes the boundary layer flow on the top surface, which is negotiating a positive pressure gradient. Mind it, it could be a positive pressure gradient beyond a certain point, and it is of course encountering a sharp turn. This energization prevents the flow separation and consequent loss of lift. So, it is almost like saying that there is a high velocity jet which is meeting the boundary layer over the leading edge flap, and because of the presence of this high velocity jet, this boundary layer becomes energized. The detailed design, of course, of the slot contour is very critical, and it must be done carefully and accompanied by wind tunnel tests. We already discussed about this concept of when we deploy the single element configuration, it is most often during the cruise. So, during the last few lectures, we have discussed about airfoils broadly, and sometimes we have dealt with it from the point of view of potential flow, while some other times we have dealt with it as a real flow, which is viscous. So, when we dealt with it as a potential flow, we remember that the flow is devoid of viscosity, it is inviscid, frictionless, and therefore, the flow actually can slip on the airfoil surface, or for that matter any other surface which is immersed into an inviscid flow. While in a viscous flow, you have formation of a boundary layer and a wake which moves further downstream of the airfoil. And when you look at the velocity distribution in the wake of the airfoil, you will see that the velocity dips when you move into the wake region, which is immediately downstream of the airfoil trailing edge. So, there is a deficit in momentum which is created because of the viscous effect of the boundary layer. So, you have the boundary layer forming on the airfoil upper and lower surfaces. Now, this deficit in momentum can be correlated with the drag force which is acting on the airfoil, and which is purely a viscous effect. So, in the case of the inviscid flow, we only have the pressure acting normal to the surface, while in the case of viscous flow you have pressure acting normal and additionally the shear stress acting tangential to the surface, so that it has a so called tugging action. It pulls the body back. In other words, you have both Cp and Cf here and only Cp distribution over here. When it is analyzed in more detail, the boundary layer close to the leading edge is laminar, then it undergoes transition, and in the later part of the airfoil it becomes fully turbulent. That means, it is basically a mixed regime, and it is rather difficult to consider all of the flow as laminar or all of the flow as turbulent, but for simplicity in the calculations we often do it that way, that we consider it to be completely laminar or completely turbulent when we assess the impact of the skin friction coefficient, for example. Now, airfoil is a streamlined body. On the other hand, we also encounter bluff bodies, and there are numerous aerodynamic applications also, in the sense that when you talk about the drag acting on a bus is by and large a bluff body, while airfoils, wings, aircrafts are streamlined bodies. So, when you look at an airfoil section immersed in a Reynolds number of the order of 10 raised to the power of 5 flow, you find that there may be some separation close to the trailing edge, because of which there is a wake formation behind the airfoil. And as the Reynolds number increases, you will find that the separation point moves further downstream, and thereby there could be a still thinner wake produced. If you look at the drag coefficient, it may be typically of the order of about 0.1, and you will find about 80% of that is due to skin friction drag. Maybe 20% of it is pressure drag, and the low pressure drag is because of a thin separated region. As the flow becomes more and more turbulent, which happens as Reynolds number increases, then CD, most of the CD would become skin friction drag, and pressure drag could reduce further. One reason being that the Cf for turbulent flow will be greater than the Cf for laminar flow, because of a fuller boundary layer, and the pressure drag could be still smaller because of a still thinner separated region, because the turbulent flow is better capable in handling adverse pressure gradient, which occurs towards the rear part of the airfoil, and it delays the separation. At low angles of attack, the separation anyway is very small. When you look at the characteristics of the airfoil at low Reynolds number, maybe even lower than this range, you will find that when the angle of attack becomes marginally high, then there could be formation of a small pocket of recirculation, which is often called as the laminar separation bubble. So, there is separation of a laminar boundary layer first, and then after separation the separated shear layer undergoes transition under favorable conditions, becomes turbulent, and because of the increasing entrainment, more momentum percolates from the cross stream direction into the shear layer, thereby energizing the shear layer and causing what is called as a reattachment, which is basically a turbulent reattachment. It is a more robust flow now, it is able to reattach on the surface. So, this is called as a laminar separation bubble, which gives a local peak to the Cp distribution on the upper surface of the airfoil, and it enables the airfoil to sustain lift at moderate angles of attack. So, this is what is called as a laminar separation bubble. If the bubble breaks, then there could be large scale separation. This is typically a phenomena that we notice in laminar boundary layers and would occur at comparatively lower Reynolds numbers, typically Reynolds number of the order of 10 raised to the power of 4 or so. Now, let us have a look at blob body aerodynamics. If we were to look at a circular cylinder, for example, at the same range of Reynolds number, we would find that the flow separates from somewhere here, and of course, both from the upper and lower surfaces, creating a wide wake. The CD could be typically of the order of about 1.2, which is about 10 times that of the airfoil at the same Reynolds number, and a comparatively wide wake. When the Reynolds number increases to 10 raised to the power of 7 or so, we find that the wake becomes much narrower, which means the separation point has been moved further downstream, creating a narrow wake. The CD over here could be of the order of about 0.7 or so. This is called as subcritical flow, while this is called as supercritical flow. The interesting part is that in a circular cylinder, you have favorable pressure gradient from the front stagnation point up to pi by 2, and then adverse pressure gradient beyond pi by 2 in the rear region, and the supercritical flow is able to go into the adverse pressure gradient and separate much later, creating a narrow wake. As a consequence, what happens is the pressure drag drops considerably for this case. It becomes low in the case of a narrow wake, and for bluff bodies, most of the drag contribution comes from the pressure drags. So, in this drag figure of 1.2, you can imagine that about 80 to 90% of it is pressure drag, and the rest is skin friction. So, if the wake becomes narrow, the drag will come down dramatically, and that is what happens in a supercritical flow. In recent studies, what is found is that the laminar boundary layer over the cylinder goes through a small recirculation pocket like the laminar separation bubble we were talking about, turning the flow turbulent, making it a more robust boundary layer, and thereby delaying the stall. While at lower Reynolds numbers, often the laminar boundary layer separates off at a much earlier angle from the leading edge. So, if you were to look at the Cp distribution, you recall the potential flow theory, which gave Cp equal to 1 minus 4 sin square theta. If you follow that pattern, then it looks like this. This is pi by 2, this is pi. For a subcritical separation, you may find that Cp distribution for the cylinder is of this kind, where whereas for a supercritical case it dips much lower and then recovers. So, you can imagine that the closer that it gets to the theoretical pressure distribution, there is further reduction in the drag. Let us do a small problem where we can do a bit of an estimation of airfoil drag by considering some simplifications. So, we are talking about thin airfoils, and it will not be a very big approximation if we start off our calculations by assuming that we can approximate it to a flat plate, provided that the thickness, the maximum thickness of the airfoil is small and alpha is also small. And we will say that the chord of this airfoil is 1 meter. So, in our approximate model, that is a flat plate model, it is also 1 meter, and we will do the calculations based on the assumptions that the Reynolds number based on the chord length is 3 into 10 to the power of 6. Chord length of course is 1 meter, and there would be two cases that we will compute. One is by assuming a completely laminar flow on the flat plate as the boundary layer develops, while in the second case we will assume it to be a completely turbulent boundary layer. So, we had earlier discussed about this result, that the boundary layer thickness for a laminar flow would be given by 5 c by under root REC if this delta is being computed at the trailing edge of the flat plate. So, that would be 5 into 1 by under root 3 into 10 to the power of 6. So, that gives us 5 by 1732. So, that is 0.0029 meter, that is 0.29 centimeter. So, that is a very small thickness, it is about 3 millimeters thickness of boundary layer at the end of 1 meter chord length crossed by that flow. Because it is a fairly high Reynolds number flow, therefore, the boundary layer thickness is also small. Later on we will see that for the same Reynolds number, the turbulent boundary layer thickness will be considerably larger than this. Now, we also learnt about average skin friction coefficient. So, that is 1.328 by root REC. So, that comes out to be this, and remember that the flow wets both upper and lower surfaces of the plate, and therefore, total CF is equal to 2 times CF bar, which is 0.0015 approximately. So, that is an assessment of the skin friction. If we assume the flow to be completely turbulent, we first need some kind of an empirical correlation for the boundary layer thickness, because unfortunately, in the turbulent world we still do not have any closed form analytical solutions available. At best we have some correlations, and if more details are required, then one has to deploy the different tools like computational fluid dynamics or experiments in wind tunnels to get more practical data. In computational fluid dynamics, for example, you may use tools like RANS, LES, DNS, to compute the data, but here we are going to make use of some correlation. So, for the chord length, this turns out to be 0.37 into the chord length itself by REC raised to the power of 1/5. So, for laminar boundary layer this was 0.5, while here it is 0.2, mind it. So, that turns out to be, so that is approximately 0.019 meter, that is 1.9 centimeter, which is way thicker than what you had for the laminar case. So, this is the boundary layer thickness. How about CF? It gives a correlation. So, what you have is 19.74. So, that is 0.0037, and the total CF would be twice as much. So, that will be about 0.0074. So, which is almost 5 times that of the laminar case. So, through this simple calculation we were able to illustrate that the turbulent boundary layer would create much larger skin friction, but then the advantage of having a turbulent boundary layer is also very obvious. The boundary layer will be much more robust in encountering adverse pressure gradient, and therefore, often preferred on configurations where flow separation can deteriorate the lift performance of an airfoil. So, we will end the discussion by having a brief look at airfoil and wing trailing edge noise. So, when we talk about noise, we bring in the issue of aeroacoustics, which is the study of flow induced noise. So, we have a flow occurring on an airfoil or a finite wing section, and then we have some noise produced by the flow itself. So, that is a flow induced noise, and this is generated either by aerodynamic forces acting on a surface or flow turbulence that often interacts with surfaces when it impinges. So, when flow turbulence interacts with a surface, the flow turbulence generates chaotic or random pressure fluctuations, and mind it that the pressure fluctuations are responsible for creating the noise. So, it is not the steady pressure, but rather the fluctuations which will make the noise happen. So, when the pressure fluctuation caused by turbulence vorticity in the boundary layer formed over an airfoil or wing are scattered by the sharp trailing edge, that is why we are talking about the trailing edge problem. Acoustic energy is generated. So, it is like sound is being dissipated from that point, and it propagates to the far field. So, it is not only created there and it is sustained there or in its neighborhood, but it propagates far away from there. So, this trailing edge noise is emitted from different kinds of aerodynamic surfaces like aircraft wings, turbomachinery blades like blades of turbines and compressors, wind turbine blades which often can be very large and are extremely important in today's perspective of renewable energy generation. Also helicopter blades, and they are dominant at high frequency. So, it is a high frequency generally broadband noise as we say. This trailing edge noise is a key element that annoys human beings. This becomes particularly important when aircrafts are landing or taking off, because they fly at lower altitudes and close to human habitat. So, it is an environmental issue which has to be tackled with a lot of care, and therefore, a lot of research is going on the trailing edge noise problem using analytical means, computational means as well as experimental means. So, in wind tunnel experiments, noise reduction and evaluating the effectiveness of various noise reduction devices has been studied widely. They have tried serrations, slits, porous materials, finlets, and different ways of boundary layer control, which are often called as active control. So, there are two means, basically passive and active flow control. So, different means of flow controls have been tried to suppress these turbulent eddy structures or vorticity structures in the boundary layer, and from them emitting noise from the sharp trailing edges. So, with these devices, about 5 to 10 decibel noise reduction has been achieved in laboratory environment, and about 2 to 5 decibels noise reduction has been achieved in actual products. So, in future more and more of these devices would actually come into practice, so that there is further suppression of trailing edge noise from airfoils and wings. So, this is a very interesting reference where you would find more details on this. So, in this lecture we discussed about the leading edge flap, and then we talked about the single and the multi element configurations. The effect of laminar and turbulent boundary layer was elaborated both on streamlined as well as bluff geometries, and we did simple calculation on flat plate to demonstrate the difference in the CF, considering a completely laminar boundary layer and a completely turbulent boundary layer. And finally, we did a brief discussion on trailing edge noise and means of suppressing that, and how they are relevant in the context of airfoils and finite wings. Thank you.